I will start this lecture with definition of turbulence, then I will cover turbulence scales and turbulence intensity, and then we'll talk about flow structure interactions, specifically what is flow separation, conditions of flow separations, and what is Struhel number. Designing a tidal current turbine, an engineer needs to estimate hydrodynamic loads on the turbine due to turbulence in order to maximize power generation, minimize premature failure of the turbine, minimize conservatism in the design process, and also to maximize commercial viability of the tidal turbine and extend structural life of the tidal turbine. Let's start with definition of turbulence. As most boundary layers encountered in practice are turbulent, it's important to know the definition of the turbulence. What is turbulence? The key qualities of turbulence are, first of all, the flow is disorganized, seemingly random behavior. The flow is also non-repeatable, so it's sensitive to initial conditions. If you change initial conditions, then you may have completely different turbulence characteristics of the flow. There is also large range of lengths and time scales, enhanced diffusion or mixing, and also enhanced dissipation. The flow is three-dimensional and rotational, and it's intermittent in both in space and time. There are two main flow regimes, laminar flow and turbulent flow. In turbulent flow, there are eddies that have different characteristic lengths and different characteristic velocity scales. For largest eddies, the characteristic length is proportional to the depth of the water column. Commonly, the characteristic velocity is taken to be proportional to the shear velocity. You already know that the shear velocity is the velocity scale of the bed shear stress. The smallest eddies within the turbulent flow are controlled by viscosity. These eddies are responsible for dissipating kinetic energy into heat. If you imagine the flow for laminar flow, all streamlines are moving parallel to each other. You can visualize the flow by injecting dye into a flow, and all streamlines will be parallel to each other. When you have turbulent flow, you have a lot of eddies generated within the flow with different characteristic lengths and different characteristics velocity scales. And there is a lot of mixing occurring, and those eddies are of different size. And the smaller size, as I already said, is controlled and determined by viscosity. Turbulent eddies create fluctuations of instantaneous velocities. Let's assume you have measurements of instantaneous velocity at a point or a period of time, 30 seconds, for example. So by black solid line, I show instantaneous velocities. I calculate time averaged velocity, and I define this with u over bar. Then I can calculate fluctuations of instantaneous velocity as instantaneous velocity minus time averaged velocity. So from this equation, you can see that fluctuations of instantaneous velocity can be positive and also negative. Turbulent intensity is one of the most important parameters used to quantify the magnitude of turbulent fluctuations affecting tidal current turbines due to its effects on the generated wakes, turbine power, and thrust coefficients or structure fatigue. And turbulent intensity is given by the following formula as shown on this slide. And when we have large values of turbulent intensities, this indicate high level of turbulence, and this can increase risks of mechanical damage of the tidal current turbine. Therefore, engineers need to take into account the value or level of the turbulence, which can be expressed through the values of turbulent intensities. A relative turbulent intensity is also quite commonly used, and usually normalized turbulent intensity is normalized by the shear velocity. As you know, velocity is the vector, And commonly, velocity is considered in terms of three components: longitudinal direction, vertical direction, z, and transverse across the flow direction, y. And turbulent intensity is given, normalized value is given by turbulent intensity, and I show with index I, depending on which component of velocity I consider. So it could be sigma u, sigma v, or sigma w, normalized by shear velocity. Or turbulent intensity can also be normalized by the time averaged or mean velocity. There is also a parameter that takes into account all three turbulent intensity quantities, and this is turbulent kinetic energy. And this turbulent kinetic energy calculated as 0.5 multiplied by sum of the square of each turbulent intensity component. Large values of turbulence intensities indicate high level of turbulence, and this can increase a risk of structural damage of the turbines, both wind turbines and tidal current turbines. On this slide, I show you an example where one of the turbines was damaged due to high level of turbulence, and one of the turbine's blades of approximately 20 meters long came off, and another was also damaged at the site due to wakes or turbulence behind the turbines. As you know that turbine intensity affects the generated wakes. So you need to be able to calculate turbine intensity and also take into account this in your design process. Let's see how flow and structure interact with each other. Assume we have tidal current flow from left to right, and flow is approaching a tidal current turbine. Let's consider only part of the tidal current turbine, which will be part of the cylinder of the turbine. When the flow is approaching, and then the flow will be moving along this solid boundary of the cylinder, then I define this axis along the flow as x. So what happens with the flow? We have development of the boundary layer, and we have velocity profile at different points when the flow is moving along the cylinder from A to B. The velocity profile slightly changed, and when the velocity is at point C, it equals to maximum velocity. Then the flow moving further downstream, we have changed velocity profile, and at point D we would have a zero velocity gradient, and then moving further downstream, velocity even becomes negative close to the boundary. So what happens? We have development of the boundary layer. Just to remind you that boundary layer is the region where velocity changes from zero up to the mainstream or approaching velocity, approximately 0.99, and this delta is the thickness of the boundary layer. And as you can see from this diagram, where I show with dashed line the boundary, upper edge of the boundary layer, and the thickness of the boundary layer is increasing. So from point A to B, because velocity at point C is maximum, we have accelerated flow. Then after point C, velocity is reducing. Then we have decelerated flow up to point C. So velocity gradient at point A, B, and C is positive. Velocity gradient at point D is equal to 0. And here we have negative velocity. Velocity gradient would be negative. Let's consider how pressure will change along this x-axis. So this is pressure change along x-axis, because here we have maximum velocity. This implies that at this point we would have minimum pressure. Therefore, our pressure will be decreasing along the x-axis and then increasing along the x-axis. So at point C, we have minimum pressure. Therefore, pressure gradient along x, dp dx, will be negative at point A, B, and C. And this is called favorable pressure gradient. And because pressure is increasing here, we will have positive pressure gradient. dp dx is positive. This is called adverse pressure gradient. Point D, where the velocity gradient is equal to 0 is called separation point, and the streamline where I show velocity is equal to 0, velocity is equal to 0 here, therefore here with this dash line I show a streamline where velocity is equal to 0, and this is called separation streamline. And within this region we have reverse flow, velocity is negative, and this reverse flow region causing eddies, and because we have different pressure in front of the structure and behind the structure, this affects the drag force. Point D is called separation point, so velocity gradient at this point is equal to 0, therefore wall shear stress is also equal to 0. And the separation or flow separation is the flow pattern when the fluid moving over the solid surface no longer remains attached to this surface. And because of this we have reverse flow causing the eddies because of flow separation. So let's see what are the conditions required to have flow separation. Assume we have flow from left to right, and then we have an obstruction, and see what happens. The pressure along the flow is increasing. Here the pressure is much greater compared to the pressure on the left. Therefore, we can ask ourselves, will we have a flow separation? Answer would be no, because although we have the presence of the adverse pressure gradient, because the pressure is increasing along the flow, therefore the pressure gradient will be positive, we will not have flow separation, because it's only one condition that is in this example. Let's consider another example and what happens in this example. Assume we have flow again from left to right, and then we install a splitter plate in the flow, and we have flow separations on both sides of the splitter plate. So what happens? Now we have flow separation. So what condition, another condition we have that we have flow separation? First of all, we also have the presence of the adverse pressure gradient or positive pressure gradient along the flow. In addition, what we also have the presence of a retarded layer of fluid next to a solid boundary, which is our splitter plate. So we have boundary layer development on both sides of the splitter plate, and therefore, because we have two conditions, we have flow separation in this case. So two conditions required: the presence of the adverse pressure gradient and also the presence of a retarded layer of fluid next to the boundary. There are two types of flow separations. First example, when we have smooth boundary, and this is flow separation from smooth boundary, and this flow separation pattern depends on the Reynolds number, and also there is flow separation when we have sharp boundaries. And for sharp boundaries, the flow separation does not depend on Reynolds number and always occurs at the same point along the flow.